Okay, in this video we're going to look at unique factorization. So the number that Hardy and Wright choose to demonstrate this is the number 666. So if we look at that, 666, the smallest prime factor that is a divisor, or the smallest prime divisor of 666 is 2. So if we take out a factor of 2, we're left with 333. 2 times 333. 333 can be factorised by removing the factor of 3 next, leaving 111, and 111 still has 3 as a divisor and leaves 37. So 37 is a prime number, and so are 2 and 3. So we're finished factorising 666, and we've determined that the prime factorisation of 666 is 2 times 3 times 3 times 37, and we can group the 3's together as 3 squared, and we get that 666 is equal to 2 times 3 squared times 37. Now that is just one particular number that we've chosen. 666 is not a prime number, but we've found the prime factorisation of it, demonstrating for this particular case, this particular number, theorem 1, which says that every number can be expressed as a product of primes. Theorem 1 doesn't get into the question of whether that expression is unique, so we're going to look at that in this video. And the first thing we want to define is something called standard form. So if we have a number n and we want to factorise it as a series of primes, we'll have the first prime number, or the smallest prime number, smallest prime factor, call that p1, and it will be raised to some power a1, and then we can have the second prime factor to some power a2, and so on, all the way up to the last greatest prime factor, pk, to some power ak, and we call this standard form. So now we're going to look at theorem 2, which is also known as the fundamental theorem of arithmetic, and this relates to what we've been talking about with unique factorization. So theorem 2, or the fundamental theorem of arithmetic, says that the standard form of n is unique. So apart from rearrangement of factors, the order the factors appear in, n can be expressed as a product of primes in only one way. So that's the fundamental theorem of arithmetic. As the name suggests, it's a central and very important theorem. We're going to defer the proof of it for now, except to connect it to theorem 3. Theorem 3, otherwise known as Euclid's first theorem, says if p is a prime number and p divides the product ab, then p must divide either a or p must divide b. So this is quite a simple theorem, which again we won't prove right now. Hardy and Wright don't prove these theorems until chapter 2, and we'll follow their progression as well in these videos. But the thing we want to note first of all is that we can extend theorem 3 as follows. So if theorem 3 says that if p divides a times b, then it must divide either a or b. If the product is a product of more factors, a up to L, say, and p divides this big product, and p must divide p must divide either a or b or c or so on up to L. It must divide at least one of those numbers, and that's an obvious corollary of theorem 3, which we can use to get closer to theorem 2. So here we can see that I've written the number n, and I've assumed that I can express it in 2 different ways. So we're looking for 2 different prime factorizations of the number n. So the first prime factorization, I've used the numbers p1 up to pk for the prime factors, and each prime factor has an A1 up to AK, and the K just tells you, the K just labels which factor you're on, and the A itself, the number up here, is the multiplicity of that prime factor in the product. And I've assumed that there's some second prime factorization where I've used Q instead of P and B instead of A for the powers of the prime factors. So the first thing to note is that any P factor must be a divisor of this product of Q's, and that's true for every P factor, and therefore it must also be true that every Q divides this product of P factors in such a way that these have to be in one correspondence with each other. The number of factors for one thing, i.e. the maximum value J or K and K must equal J, in other words, and the order that they come in must also be the same. So P1 must be less than P2, must be less than, and so on up to Pk. And lastly, in order to prove that these are exactly the same factorizations, we have to show that each index, each power is the same. So we want to show that A1 is equal to B1, A2 is equal to B2, and so on. So in order to show that, we'll start by assuming that one of the AI's is greater than one of the BI's. So if we divide out by that PI to the BI factor, the left hand side that we're left with, we'll have the P1A1 up to PI. So this PI is going to be deducted BI powers of PI. So its new power will be AI minus BI, and then we continue up to the PK to the AK. The right hand side will have P1 up to PK, but the PI BI term is missing, so it goes up to PI minus 1, and then it skips to PI plus 1 up to PK. Now the left hand side is divisible by PI at this point, but the right hand side is not, and that's a contradiction. And similarly, if we assume that BI is greater than AI, we get the same problem on the other side. So we can't escape a contradiction here, so we have to conclude that AI equals BI for all I, and therefore these factorizations are entirely equivalent. And Theorem 2 said that any number n can be expressed as a product of primes in one way only, up to rearrangement of the factors. So we can see that Theorem 2 follows as a corollary of Theorem 3, and we'll prove Theorem 3 at a later stage.